Okay, good morning, everyone. Okay, so welcome to our 2271 lecture. Okay, so for today, what we will do is we'll go through the topic on the timers and Pwm module. Okay, initially I wanted to squeeze in the serial interface as well, but I think it will be a bit too much and too rushing. So we will focus only on the timers and Pwm, plus we will go through the lab. Okay, so even though this Friday is a holiday, you can still try to work on it on your own first, and if possible you can also build some hardware, all right, the driver chip and so on to test it out. Okay, next week once you're able to come back to the lab. All right, so let me get started. Okay, so after that, once we go to the lab, I will also go through the project requirements. Okay, so I've just uploaded the last batch requirements. Okay, so for this batch it will be very similar, except that there is one or two more things I'm going to add in, okay, for the project element, okay, which I will explain later. Okay, so let's get started. Okay, so I think all of us have heard about the news where the NUS professor went on for 2 hours and then realized that he was on mute. Okay, so it came out in the news yesterday, I think. All right, so if anything goes wrong technically, please call me. My handphone is always beside me. Okay, don't make me carry on. Okay, and then tell me at the end of 12 o'clock that you didn't hear me or something. Okay, so anything goes wrong technically that is not resolved, then you just let me know. Okay, in case I do not realize that something is wrong. Okay, so let's get started here. Okay, so in this module, we're going to talk about timer peripherals. Okay, so timers are basically something that you are familiar with. Okay, you have seen it before in the EPP module. All right, and we know the usage of timers to count events or to measure intervals between events. All right, and at the same time for PWM generation. Okay, so in this project, we are going to use it for PWM generation for the motors, and we are also going to be using it to generate some music. Okay, so one of the requirements of the project is to play, your robot must be able to play some music while it is actually completing the challenge. Okay, so this is of course something you cannot see in the videos of the students because they already have some other voiceovers and things like that. All right, but this music is okay. So when we started the project, I think about 3 batches back. Okay, I wanted to standardize the music. Okay, and I gave everybody the Baby Shark music. And what happened was the whole lab everywhere was just Baby Shark, and everybody got sick and tired of the song. Okay, and you don't want to hear it again for the rest of their lives. Okay, so I decided not to torture you all. All right, so last batch onwards, I made it sort of free and easy, so you can play any music you like. Okay, from anywhere, doesn't matter. But as part of the requirements of the project, you need to when you demonstrate this in your final assessment, you need to play the original soundtrack. Okay, and you also need to play the music from your board and sort of show that they are similar. Right, it doesn't have to be the exact tone and pitch and all this stuff, but at least it must be somewhere close. All right, then we can accept that it is correct generation of music. Okay, so that part I will go through again, okay, when we're looking at the project requirements later on. Okay, so in terms of the timer peripherals, okay, that we have in the KL25Z, there are quite a lot of timing subsystems. Okay, the periodic interrupt timer, we will briefly look at it. Okay, the TPM, which is the timer and PWM module, is the focus of today's lecture. And at the same time, we also have low power timer configuration. We also have this real-time clock. All right, and there's an internal SysTick that is used to sort of used by the core peripherals. Okay, interesting thing is of course this real-time clock. Okay, and this is a good sort of peripheral to have within your controller, because in many cases you may want to keep track of time elapsed. Okay, maybe from the last time you powered down the device to the current time you switch on the device and so on. Okay, so in this kind of situations, you may want to have a real-time clock that can keep on clocking and giving you some update of the time. All right, so of course in this kind of situation, your microcontroller may not go into a total shutdown, but it may go into a very low power deep sleep mode with very little power consumption. But then this kind of peripherals such as your real-time clock may still be running for you to capture this information. Okay, so it's similar to, for example, your laptop. Okay, when you power down your laptop fully, okay, even if you take out your battery and later on you put in back your battery, you can still show you the correct date and time, correct? Because there is usually some secondary power source, okay, very small battery that is powering some real-time clock within the system that helps you to keep track of this information. Okay, so that's why even if you plug out everything, you take out your battery pack, you can still keep track of the date and time. Okay, but of course there is a limit to it, but in most cases that is good enough. All right. Now, again, this slide gives you a general overview of timers and counters. So the input to any counter is generally two types of inputs. One is you either have a periodic clock, okay, and this periodic clock can be an internal clock, can be an external clock, or you can also count events. All right, so for example, if I have a doorway, all right, and I want to see how many people are passing through, okay, then I can probably put some IR sensor or some other sensor, all right, and whenever the sensor is triggered, okay, when somebody walks through, I will generate some pulse, okay, and that can automatically increment or count, keep track of the count through my timer. So events or clocks can be used to increment or change the counter value. For any counter, you will have a reload value or a start value, and once the clock comes in, it will start to count. You may, in some cases, configure the clock to either go up or go down. Okay, some may have configuration, some may not, and in most cases, there will also be an automatic reload. Okay, so if I go all the way to the maximum, okay, in most cases, you will automatically reload to a preset start point and carry on again. Similarly, if I go down, okay, when I hit the lowest, I can reload and then carry on again. All right. At the same time, you will also have some PS or prescaler option. This is to divide the clocking rate even lower, okay, by some preset value. So the prescaler usually has some bits where you configure, and they give you a certain set of prescaler values which you can choose from, all right, to generate your required signal. And that can be used to again drive some other output or can generate a PWM. In most cases, your timer peripheral block would also support interrupts. Okay, so that if you see down here, interrupts and PWM need not be always together. All right, so this is an important concept. In some cases, you want the timer to generate interrupts, and then in the interrupt service routine, you want to carry on some activity. Okay, but in other cases, you're not interested in interrupt. You just want the timer to generate a fixed PWM in the output pin. Okay, so it all depends on what you want, and you can configure both or just one of them. All right, they did not have to come together all the time. Okay, so let's look at the periodic interrupt timer first. Okay, so this is one of the very basic timers that the KL25Z provides us, and it is a counter, okay, that generates periodic interrupts, all right, by counting down from a 32-bit value. So what you will do is you will load a 32-bit value into this register, load well, and what will happen is the moment you write to it, okay, which is the timer start value, TSV, the timer start value, it will start to count down. okay, and it will count down until it reaches 0. Okay, once it reaches 0, it will can be configured to perform two things concurrently. One, it can generate interrupt for us, okay, and the other, it will also automatically reload with the starting value and then be able to carry on with the next iteration. Okay, so in this example, I first load it with a value of 1000. Okay, it starts counting down all the way until 0, then it generates an interrupt. Okay, when it hits 0, and it also rolls up again. Okay, so you can see that the periodic interrupt is generated every time it hits 0 and it rolls up again. All right, so at that next clock comes in, it will generate the interrupt and it will start again. At any point of time, you can also change your start value. All right, and that means you are now going to have a different period for the interrupt. All right, so it's a very simple and straightforward timer. Okay, if you look at the block, okay, it's just a clock with a load value register, and once I hit my 0, I will reload and I'll carry on, and at the same time I can generate interrupts. Okay, so I will not go into too much details of the periodic interrupt timer. Okay, but if you are interested to use this in your project, you can read up more on it from the datasheet. Okay, so the focus will be on this module, which is the timer Pwm module. Okay, and why do we need this module? Because we need this module to generate the Pwm signals for our motor. Okay, so the chassis and the motors and everything will be issued to you in the next lab. Okay, so when you get your chassis, okay, or from the videos, you would have seen that basically you have four motors, and four wheels. Okay, so you have one wheel here, one wheel here, one wheel here, one wheel here. Okay, so you have four wheels and four motors. All right, and how you want to configure them, all right, is up to you. Okay, I will share with you some ideas later on how you can do the connections from the microcontroller board to the motors. Okay, so these are considered suggestions. If you want to take another approach, it's also fine. Okay, but later we will discuss in more detail how you can control these four motors. Okay, now let's look at the timer Pwm module. Okay, so as usual, I will go through some slides and then we'll go back to the data sheet and so on. Okay, just so that we can relate the information from the slides back to the data sheet. Okay, so the timer Pwm module, okay, is generally the basic block is shown over here. All right, and for this timer module, okay, there are two clocking options. One is external, okay, the other is internal. All right, uh, in most cases we always prefer the internal clock because it is already there, it's readily available, you don't need to generate any external clock. Okay, but unless you have some specific uh, frequency need that is it cannot meet with any form of configuration, then you think of the external clock. Other than that, we use internal clock and then we try to play around with the prescaler values to achieve the desired frequency we want. In terms of prescaler, okay, so this is a prescaler part of it. We have again these preset configurations, which will help us to sort of scale it down to the required frequency we want. Okay, so this Pwm module is a 16-bit counter. It can be configured to count up or down. All right, and each of these counters, all right, have 6 channels. Okay, 6 channels. All right, so if you look at this picture here, you can see that this part of the configuration here, which is the prescaler, okay, the module counter and so on, these are and the input selector, these are the generic selection options for each timer. But within each timer, you have 6 different channels. So you have channel 0, channel 1, all the way to channel n. So in this case, it's 0 to 5. Okay, 6 different channels. Okay, and each of these 6 different channels can generate an output signal. Okay, each of these 6 different channels can generate an output signal. Okay, so that is what is shown here. Each channel can generate interrupts, can request DMA, and trigger hardware and so on. Okay, and we will be looking at how to configure these registers to give us the desired output that we want. Okay, now let's just go back now to our data sheet. Okay, so can you open up your data sheet? All right, and then go to chapter 31. Okay, chapter 31. Okay, so chapter 31 is the chapter that basically gives us the information on how the timer and Pwm module is functioning. Now, looking at this, so this is the block diagram that we saw just now, where we see the input clock select, the prescaler, okay, the module counter configuration, and the different channels here. Now, looking at this TPM memory map, okay, can you sort of guess how many timer modules we have? Okay, just looking at these 2 pages here, this memory map here. Can anybody tell me how many timer modules we have? Okay, so it's correct. We have 3 timer modules. Okay, how do we know that? Because if you look at the definition here, we have TPM 0. Okay, then you have a bunch of registers for TPM 0, and then TPM 1, and then TPM 2. Okay, so once you understand the sort of style in which registers are named, the convention, you can sort of make some good guesses on some of these configurations. Right. So similarly, you can see that for each of the timer, I have channel 0, channel 1, channel 2, up to channel 5. All right. So we have a total of 3 timers, and each timer has 6 channels. All right. So that means I can generate 18 PWM signals. Correct, 18 PWM signals. So can I really tap out 18 PWM signals from my board? Will I be able to, using my KL25Z board, map out and get the 18 PWM signals at the same time? Yes or no? All right. I have 3 channels. I have 3 timers, 6 channels. Okay, so 6 into 3, 18. So rightfully, I can generate 18 PWMs concurrently with this board over here. Am I able to get all 18 PWMs out on my board? Okay, so the answer again comes back to the limitation we have when we are dealing with the preset board. All right, when we're dealing with the preset board, what we need to be mindful of is what is available, these pinouts that are available. So we need to later, we need to map out, look at the mapping between the PWM channels and the different port pins and see what is really available to us to tap out on the board. Okay, so later when we are going through the lab manual for this PWM exercise, we will see how to look at the mapping, and then we will get a sense of what is available, what is not available. Okay, and these are important things you need to look at before you develop your code. All right, because you do not want to develop your code for example, timer 2, channel 3 and 4. And then later you realize that maybe this channel 3 and channel 4 is not actually available on the pin. Okay, then you need to go and change your code. Okay, and use some other channels or some other timer. Okay, so you always need to be mindful that come back to this mapping and see which are the pins available for me to use. All right, then you decide what you want to configure for. And you will also need to make some decisions later on how you want to fulfill all the requirements of the project with the pins that you have. Okay, so there are quite a few different requirements which requires GPIO, PWM, UART, and so on. Okay, and many of them are multiplexed with each other, so you need to make a decision on what you want to use. Okay, there's no right or wrong answer. As long as you know what you want to use and you write the correct code for that, then everything should be fine. Okay. So let's come back to our data sheet. All right. So we have 3 timers. Okay, each with six channels each. Now, so let's look at the timer configuration, each one of them. All right, and then later we'll go back to the data sheet to look at it from the register perspective. So the first one is the selection of the clock. Okay, so that is the configuration of the CMOD bit. So in the CMOD bit, you will select whether I want external clock or I want internal clock, and internal clock means I have also a few options. Then you have your prescaler, okay, and then the counter. Okay, like I mentioned, we can decide whether we want to do up counting or down counting. So there are some bits we will configure, okay, in the CPWMS to decide which mode of counting I want. All right, now the next is the mod value. So this mod value is basically to decide what is the upper or lower limit of my counting. Okay, that means, for example, okay, I have a 16-bit timer, so rightfully, of course, I can go from 0 0 0 0 all the way to 0xFFFF. Okay, so that is of course the limit, but in many cases you may not want to count all the way there, correct? So you may want to cut back because you want a lower frequency. So you can just say, okay, I want to count until only maybe 0x00A0. Okay, and after that I want to restart again. So I do not want to count all the way. So I want this to be my upper limit. So that is basically your mod value, the upper limit to which your counter counts. So as you see the count here, when I count from 0, 1, 2 all the way to mod, after mod I will reset back to 0. Okay, and I'll also trigger the overflow. And when that can also generate an interrupt if I want to. Okay, and then I count again. If I were to configure for the up down counting mode, that means I can choose to count up and then count down, right? That means instead of coming down to 0, I count down, okay, count up and then count down. So in that kind of mode of operation, you will count to mod, and then from mod you go to mod -1 and so on. All right. So depending on the mode of operation, you will generate the appropriate interrupt at the time. All right, and that can be used also if you want to control some other peripheral or generate some other event. Okay, so that is where the interrupts and the interrupt flags will come in. Okay, so in terms of counting external events, okay, so for example, I said that if let's say I have an external event that is happening, all right, you have a sensor you connected to some conveyor belt, okay, and you want to count the number of packages that are passing through. All right, so you can use this kind of external clock trigger to increment or decrement your clock. So you set your CMOD to 1 0. In most cases, for external clock, you may not necessarily need a prescaler. Okay, so you set prescaler to 0, and then you can decide whether you want to generate interrupts. Okay, if I hit some overflow condition. Okay, so that is in a counter mode of design. All right, so one example is you can also use, for example, if you want to connect encoders, read encoders, okay, to your motor, and you want to keep track of this count of your encoders, you can use timers also to do it. All right. Of course, another way is you can also connect it to GPIO interrupts, and whenever that interrupt is triggered, also you can keep track of the count. Okay, so there are different ways in which you can design a system, correct, depending on what is available and what approach you want to take. Now, in terms of the counting, okay, so this is the counting up sequence. So in the counting up sequence, let's say here I set the mod is equals to 4. Okay, so in this case, the mod is equals to 4. So I will go from 0, 1, 2, 3, 4. So that is the mod. Whenever I overflow, okay, whenever I overflow at that point, okay, so as you can see, the overflow bit, okay, is set whenever I transition from the mod value to the overflow. That means I do a reset. So that is when the overflow flag bit is set, okay, and that can be used to trigger an interrupt if I want. Okay, so the frequency, okay, is considered the frequency of the overflow. That means the frequency at which the overflow bit is set or the interrupt is triggered is clock frequency divided by 1 plus mod. Okay, why 1 plus mod? Because when I set mod to 4, it is actually 5 counts, right? 0 to 1, 1 to 2, 2 to 3, 3 to 4, and then when 4 rolls over, okay, when 4 rolls over, then it is triggered. So that is why it is considered 1 plus mod. Okay, so this is one way of configuring your module where you count up and then you overflow and then you start again. All right. The other approach is basically what we call the counting up and counting down mode of operation. So in this case, you have up counting and down counting. Correct? You have two parts to this. When I'm doing the up counting, I increment. Okay, so from 0, I go to 1, 2, 3, 4, and so on. When I reach okay, so this is already considered after the prescaler. Okay, because this counting is the clock comes in, I already factor in the prescaler and then I do the count. So when I say four clock cycles or 5 clock cycles, this is after the prescaler. I mean, this is the actual clock that is doing the counting up or counting down of the register. Okay, so in this case, all right, when I reach the mod value, okay, so when I reach the mod value, the timer overflow flag is set at the end, okay, at the end of it. All right, so you can see that when I reach 4, when I start to count down, okay, then at that clock edge is where the timer overflow flag bit is set. All right, so it will count down all the way to 0 and then it will count up again. Okay, and then it will set again the next time from the mod value I overflow and sort of count down. All right, so it is at the end of that tick where I switch from up count to down count. That is where I will actually set the overflow bit. Okay, so in terms of the entire period of counting, if you see here the entire period of counting from the first time where I set the timer overflow flag bit, the next time is exactly, in this case, it is 2 times mod. Okay, that means the count is exactly 2 times mod. So the frequency of the interrupts happening is the clock frequency divided by 2 times mod. Okay, so that is this up-down counting mode. All right, so in this slides, I'm showing you the different options. Okay, later on in the PWM part also I'll show you different options. But in the lab, I'm only focusing on one particular implementation, which I've already tested and demonstrated that it works fine and is good for the lab. Okay, and good for the project. Okay, but if you want to try out a different mode of operation, different way of generating PWM, that is also fine. Okay, in the lecture slides, okay, we are covering the different options. In the lab, we are focusing on one particular approach. All right, so later when you look at the lab, you will see that, okay, you are free to, of course, try another approach if you want. Okay, so for the TPM configuration, okay, these are some of the registers. Okay, so I will not go through everything right now. Okay, we later, when we go back to the data sheet, we will look at what is needed. All right, in terms of status, there is a status register here to keep track of when the timer has counter has overflowed. At the same time, if any channel event has occurred. So what is channel event? Okay, this channel event, as you can see here, these are all the overflow bits. These refer to the configuration on which kind of mode I'm currently operating in. So there are 3 modes of operation. Okay, one is input capture mode. All right, that means I want to, for example, know the time at which a particular event has happened. Okay, so maybe I start the timer, and okay, so maybe over here I say I start a timer, and then uh, I wait until some pulse comes in, and then I stop. All right, so if I am currently using or configuring the timer in input capture mode, the value in the register, okay, will be indicative of how much time has elapsed from the time I started the timer to when the event has occurred. Okay, so if I want to capture okay some time duration between some edge, okay, and another event, then I can use input capture mode. The other is output compare mode, where I can say that whenever the timer reaches a specified value, I can do something to the output. Okay, so I can use this to make a pulse of specified width. Correct, so I can say that okay, I configure the thing to toggle. All right, so maybe every time the timer hits a value of 50, all right, then I say that the output pin toggle, so it keep on toggling every 50. Okay, so you can think of output compare mode as also a way in which I can generate, for example, a PWM, but it's a bit more tedious because I need to, I mean, firstly, if I use it for PWM, if it's a 50% PWM, then no problem, correct? Because it's always the same time for high duration and low duration. All right, but if I want to have different type of duty cycle, then it becomes a bit more tedious, because then I need to keep modifying the value to know when to toggle. Correct. All right. So output compare mode is also another way in which you can still generate a PWM signal, but it's a bit more tedious if you have different duty cycles. Okay. The one that we are going to be focusing on is the PWM. All right, which is very useful for us to drive our motors. All right, for the project. At the same time, to also generate the musical tones, okay, that we need to play for the project. Okay, so in terms of channel configuration, again, there are some bits here. Okay, so these bits here, the MSB, MSA, and ELSB, ELSA, to select the mode as well as edge select. All right, so these are important. All right, for us to decide whether I'm using the what type of PWM I'm going to generate. Okay, the mode of operation. So we'll look at that now. And of course, the Cnb register is also used to decide the duty cycle of our generated signal. Okay, so all of this is what we're going to be looking at now. Okay, so the principle behind PWM, I don't think I need to go through. Okay, yeah, I think all of us know that, correct? We basically want to generate an equivalent analog voltage across the pin using a modulated digital signal. Okay, so when your PWM signal is low, the average voltage seen at the output pin is also low. Okay, so maybe this, if I say this is 0 volt and this is 3.3 volt, okay, then maybe this is around 1 volt, maybe. Correct, so this would be exactly in the middle, correct? Okay, this will be in the middle, and this will be something higher a bit. Okay, so the PWM signal is a way of generating an equivalent analog voltage, okay, using the digital signal. Okay, so that part we know. So in our Tpm module for the KL25Z, okay, what we need to do is we need to decide what kind of mode of operation we want. So there's two types. Okay, so one is what we call the edge aligned PWM signals. In the edge aligned PWM signals, the counter only counts up. So the counter counts up, okay, up to the period. So this period is defined by the mod plus 1. So this is the period. Okay, and we'll carry on. The pulse width is decided by the Cnb register. Okay, so there will be a Cnb value that you need to update, and that will decide the duty cycle. So you will decide, okay, whenever the counter value matches CNB. So whenever it matches CNB, what to do? All right. So there's two types of waveform you can generate. So one is when it matches, I will toggle from high to low. Okay. So this is the period. So it'll be here. Okay. Something like that. Okay. Or the other one is the inverted waveform where it will be, it will be high first, then low. So it will be the same thing, but whenever it is a match, it will do the inverse logic. Okay, and this selection is actually over here. All right, whether I want high true or low true. Okay, so this bits configuration, all right, we will see later on in the data sheet as well on how to configure. Okay, but this is the mode of operation. This edge align mode of operation is what I'm going to demonstrate to you later. Okay, and it's also what is expected in the lab. Okay, but if you want to try the next mode, okay, which is the center align PWM, is also fine. Generally, either way is fine because in both cases you will generate PWM signal and you are able to control the PWM signal. So that gives you control over the motors. Okay, so either way is good enough for our project over here. Okay, so in this mode of operation, basically you are counting up and down. Okay, so it's similar to just now the picture we saw. So we're going to count up and down, and what you're going to do is this value will be your final, is your mod value. So this is your period. Right, this is your period, the 2 times mod. Okay, now your pulse width is your CNB. So this is your CNB over here. Okay, so your CNB is over here. So this will decide your sort of duty cycle of your PWM waveform. Okay, so again, whether it is this way or the other way is dependent on the configuration of these bits over here. All right, so these are all the, so I'm looking at all the bits, okay, that we need to configure. Later we will be looking at it in the register itself, okay, and we look at the code in a while as well to understand how everything comes together. All right, now so before we go on to the data sheet, all right, and look at the registers, let's review the LED strip that you got. Okay, so last Friday you got an LED strip, a small LED strip. Okay, if you did not come on Friday, last Friday, and you haven't got it, no problem. Okay, we will still issue to you once you come to the lab. Okay, so what is that LED strip for? Okay, so let me show you a video here. Okay, so the LED strip, okay, is basically, okay, so let me play this video here. So you can see that this LED strip is actually just a collection of LEDs packed together. It's all packed together over here. All right, and this LED strip can actually be used in place of your individual LEDs. All right, so as part of your project, you need to have some LED effects, some running LEDs, some blinking, and so on. Okay, so that is why you have those LEDs. Okay, you can choose to build it using or implement it using that the breadboard and individually connecting the LEDs. All right, or you can also use this particular sort of LED strip, okay, to put everything together very compactly. Okay, so it's up to you. All right, this is of course not originally part of your packing list. Okay, and this I got it because about 1 year back there was this lab in EE that was closing down. All right, and then so we just got some news that they are closing down and they want to clear everything that they currently have. So it was like a free for all. So I went to grab whatever I could. Okay, so in one of the things that I grabbed was this box of LED strips. Okay, so I think it's quite nice. All right, you can use it. You can choose not to use it, it's up to you. Okay, but this gives you another alternative to fulfill the LED requirements. Okay, so that is what you can use it for. Okay, so let me go through the datasheet first. Okay, on the timer module. Okay, and then we will go to the code after that. Okay, so this is your status and control register. Okay, and if you look at status and control register, it has a few important things here. One is the selection of your alignment of your PWM, the CPWMS bit. So that is to tell us whether we want to operate in just up counting or up and down counting. Okay, so that is one. Next is the clock mode selection. Okay, so whether we are using the clock or whether we are using it in a counter mode or in a timer mode, that means either external or internal clock. And of course, the very important thing is the pre-scale selection. Okay, so this pre-scaler selection is important, so you know exactly what frequency we are going to clock our timer at. Okay, the next register is this. This is the Tpm CNT register. So this register is actually holding the counter value. Okay, while it is counting. Okay, so while it is incrementing or decrementing, the actual value is actually stored here. We don't actually need to read this register, correct? Because we are not doing some polling, correct? We're not polling this register to decide what to do. We are already pre-configuring the behavior that, okay, when the counter reaches a mod value, I will do something. When it reaches a CNB value, I will do something. Okay, so we are already sort of pre-configuring the behavior. So this count register is used within the hardware. Okay, but if you want to read it, you can still read it. Okay, so the mod register is the one that I said just now, where it depends on, it basically sets the limit. All right, so what is the upper limit where I count to, and after that it will overflow, all right, or will start to count down. Okay, so that is the mod register over here. Okay, and the other one is the CNSC register. This CNSC register is basically to configure the mode of operation. So this is where you have the input capture or output compare, like we saw just now. So we're not using these two options, input capture and output compare. The two options we have are the edge aligned PWM or center aligned PWM. Okay, what I'm going to demonstrate to you is the edge aligned PWM. So for that, you need to configure the MS NB and A bits to 10 and the ELS B A bits to 10 as well. Okay, so these are the important configuration bits and registers you need to take note of. Okay, so yeah, the CNB register is this. So this CNB register is used to decide on the duty cycle. Okay, because if you recall here, whenever I have a match with my CNB register, that is where I will decide to do the toggling. So the CNB value is the one that holds the information on the duty cycle that I want. All right, the mod is the period. Okay, so these are the important registers we need to factor in. Okay, now okay, and this is the status register. Okay, so status register, we don't need to worry about it so much. So for now, because we are going to be using the interrupts and the hardware configuration to just generate the PWM for us. Okay, okay, so that's what I want to show you for the datasheet part. Okay, so this question here is important, all right, because that is going to drive our whole code that we are going to build for the lab. All right, so the question is this. Okay, we want to use timer 1, channel 0 and channel 1. Okay, so we have 3 timers, timer 0, channel 1, channel 2, and from these 3 timers we have 6 channels each. Okay, and what I'm telling you now is I want to use timer 1, channel 0 and channel 1 to generate the 2 different PWM signals. Which ports and pins are they mapped to, and which ports and pins should I choose? Okay, so this is the question I'm going to leave you with. Okay, while we go for a break. Okay, so now it's 10:50. Okay, let's go for a break at 11 o'clock. Okay, 10 minutes time, I'll see you back here, and then we will discuss this question. Okay, and why this is important before we even start looking at the code. All right, so I'll see you all back here in 10 minutes. All right, and then we will discuss this. Okay, so welcome back. Let's carry on. So we stopped at this question here. That we want to use timer 1, channel 0, and channel 1 as the PWM signals. So which port pins are they mapped to? All right. So the first thing is, for this first question here, which port pins they are mapped to? All right. We should know that the place to refer to is the signal multiplexing. Okay, the signal multiplexing, I showed you this before. So if you look at this signal multiplexing and pin assignment, that is where you have all this information on the pin name and the alternate functionality. All right. And so what you need to do is you need to scroll through, all right, and look at the alternate functionalities, all right, and see where is timer 1, channel 0, channel 1. Okay, so if you see down here, timer 1, channel 0, channel 1 is mapped to port E20. Okay, so if you look down here, okay, channel 0 and channel 1 is mapped to port E, pin 20, and pin 21. Correct? So that is one possible option. Okay, so let's note down this. All right. So what I want is, okay, let me move this first. Okay, so what I have is, I want timer 1, okay, channel 0 and channel 1. Okay, so this is what I want. So one of the options, okay, from the datasheet that we see is I can use port E pin 20 and port E pin 21. Okay, so that is what right here. So port E20, port E21. All right, and while looking at the port numbers, you should also take note of the alternate number. All right, the alternate number. So for this port E20 and 21, this is tied to alternate 3. Okay, this is tied to alternate 3. So I need to also take note of this information that this is alternate 3. Okay, alternate 3 functionality. Okay, so that is one possible option. Correct? Now the next thing is, okay, let's scroll down some more and look at where else we see timer 1, channel 0, channel 1. Okay, so we see timer TMP1, channel 0, channel 1. Okay, so I see over here again, tied to port A, pin 12, pin 13. Okay, port A, pin 12, pin 13 is also a viable solution. So I'm going to write that down here. Port A, pin 12, and port A, pin 13. And for that also, it is considered to be a alternate, just confirm, alternate 3 function. Yes, there is also a alternate 3 function here. Okay, so this alternate 3, if you remember from your GPIO Studio, okay, it is to configure the pin. Because each pin has various multiplexing options, so we need to select the correct alternate option depending on what we are using it for. Okay, so let's go down some more and see where else we can get it. Okay, so over here I have again port B0 and port B pin 1. Okay, port B0 and port B pin 1. Okay, so this is port B0 and port B1. So again, this is also the alternate 3 and alternate 3. Okay, so is there anything else? Okay, so maybe there are others, okay, but for now, this is what I see, all right? Okay, so when we look at all of this, what is the important thing we can take away from this? That when I want to use a certain peripheral block, okay, for the KL25Z, you have actually a lot more flexibility, okay, to decide which pins you want to use, because the same peripheral block may be mapped to a few different pins. Okay, so it gives you a lot of flexibility, okay, to choose what you want. Okay, but at the same time, you must remember that when you choose one alternate function, you are automatically saying that you're not going to use it for other alternate functions, correct? All right, and that is a very important consideration that you need to take into account. So for example, if I go back here and I say I want to take port E pin 20, pin 21. So if I use my timer 1, channel 0 and channel 1 for PWM, and then I cannot use it for my UART module, because my UART module, UART0 module is mapped to the same two pins. Okay, so I may have to use UART2 module. Okay, so you need to take into account that every decision you make on selecting one particular functionality, you must now look at other pins, okay, for other functionality. Okay, so it all depends on how you want to decide, okay, how you want to design your whole system. Okay, so for our lab manual, this is the option that I've chosen. Okay, I'm going to go through with this option. Okay, you are free to try other options as long as your configurations are correct, your code is all done correctly. Whichever option you choose will still work. Okay, but in the lab, I've chosen this configuration and this is what we're going to go through. Okay, so let me go through the code. Okay, so in the code, okay, from the lab manual, okay, so the first thing is we are going to call this function called init Pwm. Okay, so in this init Pwm, we're going to do a few things. Okay, so let's go through and understand step by step. Okay, so the first thing is, since I'm using, okay, I'm using port B. Okay, I'm using port B, pin 0 and pin 1. Okay, the first step I need to do is I need to make sure that I enable power to port B. Okay, so that is the clock gating part. All right, so this is what I mentioned, where what you have learned before, you still need to apply. All right, so the clock gating for each peripheral subsystem, you still need to do. If you forget this first step, then all the other code that you write is not going to do anything, correct? Because there's no power to the module. Okay, so the first step is you configure the power. Okay, make sure that the peripheral subsystem is powered up. Okay, the next step is the Pwm configuration. So this again we have done before, but in this case we need to make sure that we choose the correct mark setting. Okay, so we have already gone through all this macro in the GPIO Studio, so I'll not go through that again. Okay, so when I say port PCR mux 3, basically I'm configuring the mux bits to say I'm selecting the mux 3 option. Okay, and for based on the table in the datasheet, we see that the timer functionality for both port B0 and port B1, both of them is tied to mux 3. Okay, so you need to check the table to know exactly which multiplexing option you are now selecting, okay, for that pin. Okay, so this part I think you are familiar with. All right, so now let's come to the part where it is more with the timer. So the next is I need to enable the clock gating for the timer module. All right, so this is another important thing you must know. All right, when you are dealing with peripherals, you need to enable power to the GPIO block to configure the GPIO mark settings. At the same time, you need to also enable clock to the peripheral subsystem you are targeting to use. So in this case, we are using timer 1. So I need to make sure that I enable clock gating for timer 1. So that is inside the SCGC6 register. So if I go and search for SCGC6, okay, you will see that this register has all the clock gating bits for the timer modules. Okay, TPM 0, 1, and 2. Okay, so in our case, we are using TPM 1. So that is what I am doing here. Okay, so that is this line over here to enable the clock gating for the timer 1 module. All right, so right now we have already configured the GPIO. We have already enabled the timer. Now we're going to go into the specific details of what we need to configure for the PWM operation. Okay, now if you look back at the slides, okay, if you go through the sequence, okay, so the first thing is what? The first thing is your CMOD. You want to configure your clocking device or clocking source, either internal or external. So that is where your CMOD comes in. Okay, so your CMOD is inside your Tpm SR SOPT2 register. Okay, so let me show you that over here. So it's inside here, status and control register. Tpm Csc, you're configuring the CMOD over here. So if I, let me come back to the code here. So the clock, okay, is inside this SIM. Wait, okay, sorry, there's a different register. Give me a minute here. Okay, so this is the register. So this is the timer clock source selection register, system option register to SOPT2. All right, so inside this register is where you decide the clock for different peripheral subsystems. So you can see that your UART can be powered by different clock, okay, your TPM by different clock, by USB by different clock, and so on. Okay, so this is the main sort of switch that decides which clocking source is used for your peripheral block. Okay, so the default one that we're going to be using is the 01 option, which is the MCG FLL clock. All right, so this is the system clock, and by using this clock, I've already done the measurements and calculations, which I will show you in a while. Okay, so by sticking to this configuration, you can follow through with the same approach that I have shown you. All right, so this is the main clock that is going to drive the system. So that is why the TPM SRC here, I have configured it to a value of 1. Okay, so that is the first part. All right, so that configures the main clock that is going to drive the Tpm module. Okay, now the next thing is your TPM1 status and control register, SC register. Okay, this mod value, I'll come back to this later. So let's come back to this first. These 3 lines over here where we are configuring the S and C register. Okay, so let me come here. Okay, so that is this register here. Okay, the status and control register. So in this status and control register, you can see that what I'm doing here is I'm configuring the CMOD bits to a value of 1. Okay, so the CMOD bits to a value of 1, what does it do? Okay, so when the CMOD bits here a value of 1 means, okay, it says that the timer is going to increment, okay, on every counter clock. Okay, so this is your normal default way of operation, where I'm saying that this field is just going to keep on incrementing. The timer is going to keep on incrementing every input clock that it receives. So the input clock is coming in, okay, from the clock that we configured just now, the system level clock. Now, in terms of Pwm mode of operation, like I said in the slides just now, we are going to be using the default up counting mode. Okay, so we're going to be using the default up counting mode. So we're not going to go up and down. We just up and then go back to 0 and count again. All right, so this is the CPWMS bit. Okay, so the CPWMS bit by default it is 0. Okay, so I am not actually configuring that bit over here. Okay, but it is by default 0, so it is already configured to be edge aligned PWM. Okay. The next is the prescaler bits. The prescaler bits I'm putting in a value of 7. All right, so if you look in your data sheet here, value of 7 for this prescaler field is equivalent to 128. Okay, so I divide the clock that is coming in by 128. Okay, so that are the current settings that I have. Okay, and this Align Pwm. Okay, so I'm actually clearing the bit over here, but even if you don't clear it, by default it is still 0. Okay, but this line here is actually clearing the CPWMS bit. Okay, so the CPWMS bit is what I said just now, to ensure that I am operating in the up counting mode for the PWM. Okay, now that we have all of this, let's come back to our mod. Okay, so the mod value is basically the maximum value, correct? So if you remember, we said that I will start off with 0, correct? And I'll count until I hit the mod value. Okay, so this duration basically tells me the frequency, okay, of the PWM. Okay, the frequency of the PWM. So what is the frequency that I want? All right, so we know that, okay, so in this code here, one of the things you need to do is up here I mentioned that you need to include clock setup 1 to change your core clock frequency to 48 megahertz here. Okay, so in this case, okay, the clock setup 1, changing the core clock to 48 megahertz is inside this file, system mkl. Okay, so that is inside here. So over here, once you set clock setup to 1, okay, you will operate at 48 megahertz, the default system clock. Okay, again, these are all just to make sure that we can relate the timing parameters that we are seeing with the calculations. Okay, so you can see the relationship. Later on, you want to change the frequency to the default or what is fine. All right, because the PWM, of course, is used to generate a particular frequency. All right, when you are talking about the musical notes later on, then you of course need to make sure that you have the correct frequency generated depending on the clock frequency that you're running on. Okay, so it is something you can change, but if you change that, then you also need to factor in the values you use later on for the musical generation. Okay, now, so since we know that I'm running my core clock at 48 megahertz, okay, and then I'm going through a prescaler. Okay, that means my main clock is coming in at 48 megahertz. Okay, so I have a 48 megahertz clock coming in, and I go through a prescaler of 128. All right, so after I go through a prescaler of 128, I have a frequency of 375 kilohertz. Now, what is the ultimate frequency that I want? Okay, the frequency of the PWM. So again, that is something you can decide. Okay, for this lab, I wanted to just generate a 50 hertz signal. Okay, so I need to divide by some other number here to get 50 hertz. All right. Okay, so that number is basically the count that I must reach to generate a 50 hertz output. Okay, because this frequency of 50 hertz means what is the count I must achieve. Because every count I'm incrementing by 1. Okay, so what is the count I must achieve so that my frequency here is 50 hertz. Okay, so that value, okay, is basically you take this 375 kilohertz divided by 50, you get 7,500. So that is why your mod is 7,500. Again, this is just a value that I chose. It's nothing in particular. Okay, I just wanted to show you how to do the calculation to achieve a desired frequency. All right, if you want 100 hertz, you want 200, that's up to you. Okay, but this is just to show you how we do the calculations towards a particular frequency. So the mod value is 7,500. Okay, what does that tell us? That means when I am running at 375 kilohertz, that means my clock is incrementing at this rate. When I hit a count of 7,500, that will give me a signal of 50 hertz at the output side in terms of the period. Okay, so that is the mod value, okay, that you put in. All right, so that is the calculation for the mod. And once your mod is done, the last part is your Csc register. So coming back here, okay, the Csc registers, let me just show you this, correct? So these are the ones, okay, just now we talked about, yeah. So the Csc registers are the one that control the toggling operation, correct? That means when there is a match between CNB and the mod, okay, should I toggle up or should I toggle down and so on. All right, so that is the configuration. Now if you look back at your registers here, okay, you can see that if I want Align Pwm, all right, you can configure it as 1010 for the MSB and MSA and the ELB and ELA. Okay, that is for high true or low true. Okay, so you can try either one. Okay, in this case I've chosen the high true, okay, to represent the duration where it comes out. Okay, while it is counting up it is high, and after that it will clear once there is a match. Okay, so it will count up. Okay, so over here if I want to draw the waveform, okay, while it is counting up it will be a high and then it will be a low and so on. Okay, so that is how I have configured the CNB registers over here. I mean the yeah, the register over here for the status and control. Okay, so let's look at the code. Okay, what we have done here. So in order for me to configure the ELSBA and MSBA, first line here is to clear the bits. So this one is to clear the 4 bits there. So that's why I do an AND equal with the complement. Then I do a OR. So when I do a OR, you can see that I only set the ELSB and I set the MSB. So the A is 0. This A is also 0. So it is ELSB1, ELSBA is 0. MSB1, MSA is 0. So that corresponds to this setting here. 1 0 and then 1 0, which is Align Pwm. Okay, so this code here that you're seeing is basically configuring both channel 0 and channel 1, okay, on port B, pin 0 and pin 1 to operate in Align mode. All right, the frequency is at 50 Hertz, okay, based on the mod value. Okay, now once you have done all this configuration, that means you have already set up everything for the PWM to run. All right, now the only thing left that we have not done yet is what? The only thing left we have not done is to configure this register here. Okay, because we already configured the PWM, the output, the toggling behavior, and everything else. Okay, the only thing we have not done is specify the duty cycle. Correct, we have not specified the duty cycle. So in order for us to specify the duty cycle, okay, that is where the code in the main comes in here. So of course this code you can also put inside the setup, no problem. Okay, it will still work. Okay, I just want to put here so to show you the distinction that once I set up everything, I can just change the CNB value to change the duty cycle that I want. All right, so over here what I've done is I have configured channel 0 to this value and channel 1 to this value. Okay, what are these values? So EA6 is actually 3750, which is half of 7500. Okay, 7500 is the mod. Correct. So since I have put the mod value as 7500, okay, I've put my CNB as 3750. All right, so that will give me an exactly half, okay, of the mod value, which would be 50% duty cycle. Okay, so that is this. And then I have further divided it by 2, okay, to put it in C1B. Okay, that means this would be considered like a 25% duty cycle. So EA6 divided by 2, you get 753. Okay, so I just put in these numbers just so that you can see what is happening. All right, again, you can change these numbers depending on what is the duty cycle you want to achieve. All right, now, so let's look at this code here and see what happens when we run it. Okay. Okay, so the first thing is, of course, you want to make sure you connect up correctly. Okay, so let me bring up the camera here. Okay, so the first thing is you want to make sure you have configured it correctly in terms of the hardware. So if you look at your port B, pin 0 and pin 1, it is right here. Okay, it is over here. Okay, so you need to make sure that you have connected both port B, pin 0 and pin 1 to those pins over here. So that is what you see, okay, over here. Okay, these two pins. Okay, and these two is the ground. This two is the ground, these two are the port B, pin 0 and pin 1. Okay, so I've connected it such that both are going into the oscilloscope at the same time. All right, and if you observe, okay, let me power it up now. Okay, so if you observe the waveform, okay, you will see that, okay, let me zoom in a bit. Okay, so you can see that the first signal on top is actually your channel 0. Okay, and channel 0 is operating at 50% duty cycle. Okay, why? Because it is running at half of the duty cycle value. I mean, COV value is set as half of the period. Okay, so it's 50%. And you can see that the frequency 1, okay, you can see at the bottom of the oscilloscope there is written as 50 hertz. Okay, so that gives you the confirmation that the calculation is correct. All right, the way we calculate the mod value and the COV value is correct. Okay, for the second waveform, you can see that the on pulse here, okay, maybe I can zoom in here, is actually half of the pulse on top. So that is the channel 1. So the channel 1 on duration is actually half of the channel 0's on duration because I divided the CNV value by 2. Okay, the COV value I put divided by 2 and put into C1V. All right, so that is basically what you can observe when you run this code. Okay, so the code is actually given to you in the lab manual. Of course, you're asked to understand it, okay, and look at what is happening. All right, so what I've gone through today is actually basically to help you understand all those lab questions that you see in the manual. Okay, so when you run the lab, okay, you'll be able to generate the PWM signals that is required. Of course, what you then need to do is you need to modify and sort of generate your PWM signals for the audio part. Okay. Okay, so okay, Patsy, we ask you to capture the signals if it's possible. All right, but again, it's good to do it. All right, so that you have a feel for what is happening and what kind of signals you're getting. Okay, so for part 2, okay, for part 2 in the lab manual, I've given you some frequencies. Of course, when you're writing your own music, you will have a lot of sharps and flats and so on. So all those have different frequencies, and this is also only a particular octave. Okay, you may obviously want to extend to different ranges that you want to play. Okay, so you must be able to generate different frequencies to have the required audio signals that you want. Okay, so those are things that you can actually try at home as well. Okay, with the board and with the buzzer. Okay, the buzzer again is not really fantastic. Okay, so if you wish to buy some other speaker on your own, okay, you can of course do that. Okay, for your project. All right. So that basically wraps up the PWM module, okay, and the requirement for this week's lab. So this week's lab, of course, we can't do it in the the actual lab because of the holiday, but you can actually look at the code, and you should, if since the code is already a working code that's given to you, it should work. Okay, and if you connect up your buzzer, okay, in your lab kit, you should be able to actually hear the sound. Okay, so even if you cannot measure the signal yet on the scope and so on, you should still be able to hear some audio signals, and then from there you can try to play around with the frequencies and see the any audible effect or change in the sound that you hear. Okay, so that is for the audio part. Okay, so now let me move over. Okay, so that wraps up the Pwm chapter. So let me go through briefly the product specifications, okay, so that you have an idea of something that you're going to be doing, all right, where it all builds up to. Okay, so this is what I mentioned in the announcement just now. It is the last batch, all right, requirement. These requirements will still be retained, except I will add on a few more because there are some updates I'm doing to some of the specifications here, all right. But generally, what you see here is also what you'll be required to do. Okay, so your project, okay, what you're supposed to do at the end of it all is to design a RTOS-based robotic car that will be controlled through an app. Okay, and you will be required, okay, to make sure that you have a good quality Bluetooth connection with the Android app. Okay, and your app will be sending commands to the robot, all right, and your robot must be able to execute those commands. Okay, basically it's a remote control car, all right, that you need to be able to execute with the app. Okay, you have to move the car in multiple directions, and while your car is moving, you are also required to control different LEDs depending on the car's status. Okay, and also play different sounds and tunes according to the car status. Okay, so there are some parts that, okay, so most of the assembly you are expected to go through on your own. Okay, so the chassis and everything is quite intuitive, right? I think it's quite easy to sort of assemble on your own. Okay, and once you assemble it, okay, you can then mount your motors and your wheels and things like that. You are given the H-bridge motor drivers, okay, similar to EBP2. Okay, and I given you the link. All right, I'll explain in a bit how to use the driver as well. Okay, the interface of the Bluetooth module, I will explain to you all in more detail next lecture. Okay, because that involves the serial interface module. So once we cover the serial interface module, I will explain how to perform that part of your design. Okay, so these are some of the requirements in terms of, let's say, your motor control and LED control. Okay, so these are things that you can probably work on right now itself. Okay, if you look at motor control, of course, you're talking about PWM, and you need to control the motors. So you must be able to move in all four directions. You must be able to do curve turns. Okay, and if I do not send any command, you should stop moving. Okay, in terms of LED control, okay, you have two LED strips. Okay, or if you want to use the separate individual green and red LEDs is also fine. Okay, so what you need to do is when it is moving, all right, you have some running sequence. Okay, that means it's a running main sequence, right, left to right, right to left, and so on. Then you also have LEDs at the back, all right, where you need to make sure that you have constant flashing at different rate. Okay, so when it's moving, it is at a particular rate of flashing. When it is stationary, it's a different rate of flashing, and so on. And at the same time, you also have the requirement to play the song. Okay, so the moment you start the challenge till you finish it, the song must continue to be playing even if the robot is not moving. Okay, and once it ends, you must play some other end tune to say that you have completed the challenge. Okay, so right now, with what we have already done so far, you can actually start to work on the audio part, correct, the song part, the LED, correct, because you already know about GPIOs. And with today's material, you also understand the concept of PWM. Okay, of course, once you do the lab, you have a better idea. All right. So these are what you call the basic device drivers you can actually start to build. Okay, we haven't gone to RTOS yet. We haven't started on the multi-threading part yet, which we'll be doing soon. But the RTOS is going to leverage on all these device drivers you're going to build. Okay, so don't wait until we start RTOS, then you go and start to think of how to control the motor, how to control the LED. Okay, then it will be too overwhelming. Correct. What you should be doing right now itself is start to develop good libraries or device drivers that you can utilize very easily later on. Okay, so that means you must already have blocks of functions or code where you can say, okay, when I call this, I can move the motor in a certain direction. When I call this, I can control the LEDs in a certain direction and so on. Okay, or a certain pattern. So once you have all this ready, then when the RTOS part comes in, you just figure out the architecture and then when and where you're going to use these different blocks. Okay, so it becomes easier to build up the whole system once you have all these smaller parts ready. Okay, so that is what you should actually be starting to do right now itself. Okay, build up all these device drivers, okay, and get them ready so that when the RTOS part comes in, your low-level code for all this hardware interfacing is already done. Okay, and it's ready to be used. Okay, so that is what you should be really starting to work on. Okay, the one more part I just want to show before I end today is the part on the motor driver. Where is that? Okay, so on the Android app and all this interface and so on, that one I will talk about it next week. Okay, the one other thing that you can also start to do once you get the chassis with the wheels and the robot is to start to solder your driver chip, okay, and configure the motor libraries. Okay, so your driver 8833 chip, okay, that you're going to be using, okay, is basically same thing that you use in EPP2. All right, and the objective of this driver chip is basically to provide the additional power you need to drive the motors. Okay, so what you are going to generate from your KL25Z, okay, are your PWM signals, and the same PWM signals are just going to go in to your driver chip and going to come out. So whatever going to A in one is going to come out in A out one. Only thing is going to be a amplified version because you need that additional boost and power to drive your motors. Okay, so that is what is going to happen. Now, coming back to the idea of how to drive the motors. Okay, so we know that I have four motors, right, and 4 wheels. Okay, so I have 4 motors. Okay, and I have 4 wheels. Okay, now we have a lot of PWMs, correct? We have a lot of PWMs that we can generate. Do you really want to use 4 different PWM to control the 4 different motors? Okay, that is your choice. All right, if you want to do Fast and Furious, Tokyo Drift, and things like that, yes, you can consider doing all those kind of things. All right, but it is not necessary. All right, okay, even though we have the ability, okay, but you can actually simplify your design. Okay, if you wish, by just generating 2 PWMs. Okay, 2 PWMs where one PWM is for the left hand side and the other PWM is for your right hand side. All right, so that is one way in which you can simplify. Okay, so you can say this is for your PWM left and PWM right. Okay, so you can imagine that even though I have 2 left and 2 right, you imagine as 1 left and 1 right. Okay, and the same PWM signal is coming out. Okay, so of course when you say PWM left, PWM right, this is actually 2 lines. Correct, because you need to be able to move in both directions, forward and reverse. Correct. Okay, so that tells us that it is I mean, this is one possible option, okay, that you can actually use to configure your motors. All right, if you want to have some other design, Okay, where you say one PWM is to control the front two motors, another PWM to control the back two motors. Also can. Okay, also can. So it is a matter of what you want to do, how you want to achieve it. All right, but ultimately, as long as you can fulfill the requirements of the project, that I can move in all four directions, I can do curve turns. That means I can go forward, backward, right, left. Okay, I must be able to do a curve turn. All right, then it's fine. Whichever way you want to connect the different motors is up to you. Okay, so that is a design choice that you can make. Okay, so the resources given to you, okay, inside the project kit are more than enough to fulfill all the requirements of the project. All right, but you have the flexibility on how you want to design it. All right, in terms of the hardware, the interfacing, and so on. All right, so these are things that you can decide, okay, within your group, okay, how you want to do it. Okay, you can of course talk to your tutors, your lab TAs, and so on. Okay, get some ideas from them. Okay, how they do it, how do they manage it. All right, and then you can decide what you want to do. Okay, all your tutors and TAs are all those who just completed or completed one batch ago, so they have all gone through the exact same sequence. Okay, the same project, the same design and everything. Okay, so they are very comfortable with the requirements of the project. Okay, so they should be able to also give you some tips and advice on how they manage to put together these hardware components. All right, so these are things that you can actually start to work on. All right, so again, I'm emphasizing, please start, all right, developing all these basic code blocks that you need. Okay, LED control, motor control, audio control, and so on. Get all these basic blocks ready so that when the RTOS part comes in, it is just a matter of plugging in these blocks in the right places. Okay, so it takes some time, but once you get everything ready, you will see that it's a lot easier once the whole architecture comes in. Okay, many students wait until the RTOS part comes in and then start to write code for LED, then start to write code for motor. Okay, and then it's a bit overwhelming, correct? Because too many things at the same time. Okay, and hardware integration takes time, right? You need to put things together, you need to solder, you need to connect wires, and so on. So all of this takes time. All right, so try to plan out, okay, your work, okay, because we're already going to be having the recess week soon. Okay, and as you know, after recess week, time flies, correct? Because all your other modules, your assignments, your projects, everything will be due. All right, so everything will come together at the same time. Okay, so try to space it out and start early so that you don't feel too stressed towards the end. Okay, so I did receive some queries regarding the lab presentation. So firstly, the lab presentation, okay, if in the lab manual, even if they say you need to do lab demo and so on, those are not necessary, okay, unless I've already told you beforehand. Okay, so I will tell you clearly when you need to do a lab demo. Okay, if I do not say you need to do a lab demo, then you do not need to do it, even if the lab manual says so. Okay, so do not need to worry about that. So as long as there is no lab demo requirement, you do not need to come to the lab. You can still work remotely. Okay, so that is fine. Okay, I will tell you upfront whenever a lab demo is required. Okay, then is when you need to schedule and see when you want to come and do the demo to the TA. Okay, for the midterm date, I will send out an announcement by today, by this week to fix and finalize the date. The midterm will be conducted during our normal lecture hours only. Okay, so it will not be on a Saturday or anything. It will be a normal, the usual lecture slot. Okay, so there should not be any issue or any clash with anything else. All right, so it will be the normal lecture slot. So I will just fix and confirm the timing as well as the way in which we'll conduct by the end of this week. Okay, as well as the coverage on what topics are being tested. Okay, so that's all I have for today. Okay, so any questions you can ask me. If not, wish you all a happy New Year. Okay, enjoy the holidays, and I will see you all next week.